Okay, moving into 5.9 day 2, we're going to look at some special cases for definite integral. Definite integral. Okay, remember, when we are doing an integral or an antiderivative, what calculus is happening or what mathematics is happening is the y is getting multiplied by the x. So whatever's on the y-axis is getting multiplied by whatever's on the x. We're always called this, or I should say, under the curve. Well, you're about to find out that that antiderivative value that we get is sometimes equal to the area under the curve. So, here's our special cases. Look, first one. We're looking at the area from 1 to 4 of x squared minus 5x plus 2. dx. We're going to go ahead, plow right into the antiderivative like we think nothing special here. So we'll do our power rule on each separate term because of the power of 1 here. So this becomes 1/3 x cubed. This becomes, that'll be a 2 times halves x squared plus 2x. And then we're going to be plugging in a 1 and a 4, but the 4 first. So plugging in 4 first, and I already have all the calculator work done, so I'm not going to take the time to do that. You will get a negative 10 2/3 minus, plugging in a 1 here, you will get a negative 1/6. Well, I think you can kind of see what's happening. We're going to change this to plus a positive. This will become negative 10.5. And that's supposed to be our area. Negative 10.5 square units. How can that possibly make sense? Area is not negative. Well, these are the special cases where the actual value of the integral, this is the exact value, doesn't quite match the area, but you'll see where it comes from. We're going to see where it comes from by looking at the graph. So if I graph this, back here, y equals the original equation. We're finding the area under the original equation, which is x squared. Oops. Minus 5x plus 2. Let's do graph. I'm going to have to fix the window here. Yep. Zoom standard. There it is. So you can see this parabola goes below the axis, and we are looking at it from 1 to 4, and it happens to be that 1 is right at this intersection and 4 is here. Well, actually, not quite right. Here it is. Let's trace work on this thing. Trace. Yeah, 1 is right about here, and 4 is right about here. So when we say area under the curve, under this curve would be down here. So that's not the area that it's finding. It's finding the area between the curve and the x-axis. So if we were to think about Riemann sums here, go back. If we looked at our rectangles on the is 2. When I go to plug that into my equation to see what the height of my rectangle is, because we were always using the y value as our height, our y value is a negative value. So when the calculus is being done, all of the heights are negative. So when it's multiplying the x by the y, all of the x values are positive because they're between 1 and 4, but all of my y values are negative. So positive times a negative is what's making this integral come up with a negative value. So our special case here, the heights of the rectangles are negative, the y values, and then the bases of our rectangles are positive, which are our x values, and when we multiply them to get area, the area is coming up negative. So technically, if we wanted the area under the curve, we'd take the absolute value of that. But if we're finding just the antiderivative or the integral value is negative. It shows that direction. Okay, so that's one thing that can happen. All of your area below the x-axis makes the integral come up negative. Pi over 2 to 0. So the fundamental theorem says you always plug in the top value. So if I do that, I've got sine of 0. Sine of 0 is 1. Sine of 0, that's the y, that is 0. Minus, and then pi over 2 up at 90, sine is 1. So again, we're getting a negative value. So, is this the case that our area from between the pi over 2 and 0 is under the axis? Let's find out. So y equals, clear, cosine x. Well, you know what cosine looks like. It's a cereal bowl. Well, maybe you don't remember, but finishes at 2 pi. So 0, see, starts high, comes down. So pi is here in the middle. Pi over 2 is right here. You know where 0 is here. So it's giving me a negative value for this area right here. And that area is completely above the axis. So why is that? Well, it's with these being switched around, the change in x, it's reversing the order and giving me a negative on the change in x here. So our base numbers are coming. So the x values are going to be negative, but my y values are negative. So heights are positive. Order. It's doing the 0 minus. So, and I will see this happen where somebody will do a problem and they'll accidentally plug in the, not in this case, plug in the bottom one first, subtract the top one, they get a negative answer and they don't know why. Well, it's because you've reversed the order here. You've done this instead of the small to the big. Okay, so there's two different ways you can come up with a negative value there. Number 3, special case. So we're going to do the antiderivative from 4 to 1. So we've got those reversed. So we know right away that our base on our rectangles would be a negative value, so the x's are negative. We're going to look at the equation just negative 5 dx. Okay, well, let's look at the graph first and see if we can see what kind of an answer we're going to come up with. If I've got the equation y equals negative 5, that's just a horizontal line down at negative 5. So here's x-axis, y-axis, 1, 2, 3. Horizontal line. I'll do it in pencil. And we're looking at the area from 1 to 4. Well, this is just a rectangular area. We wouldn't even need calculus to get this. We can just out. Let's see if our area, the actual integral value, does the integral equal what should be the area? So if we look at this, the height of this big rectangle here, it's 5. The width across here is 3. Will we get a positive 15 integral value with these x values switched around? Let's think about it. If you think about finding the area of one of these rectangles, because the equation is below the axis, our height is going to be negative. Because we've got these flipped around backwards, the base of the rectangle is going to be negative. So, if we do the antiderivative, we should be getting that positive 15. Let's see if we do. So, antiderivative of negative 5 is just negative 5. We're going to plug in a 1 first. So, 5 times 1, or negative 5 times 1 is a negative 5. Minus, plugging in the 4, we will get a negative 20. Negative 5 minus negative 20 plus a positive, we do get 15. So here the integral value does equal the area because we've got two negatives happening for us. Okay, next special case. So, we want to find the integral from 1 to 3 of 2x plus 1 squared. The integral from 3 to 5 of that same equation. And then we want to find the integral from 1 to 5 of that same equation. So let's take a look at the graph first. Let's see what this is actually saying, how it's chunked up, and see if you can see where this is going. So we've got a parabola 2x plus 1 squared. So that looks like this. So it's up 1. It's a little narrower because of the 2. So it doesn't overly matter. So this first one, we are looking at the area from 1 to 3. So this chunk here. The next one is looking at the area from 3 to 5. Well, that means I'm starting here and going to 5. And the last one wants the area from 1 to 5. Well, let's think about, are we really going to have to do this last one? let's go through it. So we'll just do our antiderivative. So antiderivative is, we need, well, let me write it out here. I go 2x plus 1 squared. So antiderivative is, the derivative of the inside is a 2, so I need a 2 and a 1/2. Do a power rule. We have 1/2 2x plus 1 to the third times reciprocal. So the first one we're doing is from 1 to 3. The next one we're going to do is from 3 to 5. And the last one we're going to do is 1 to 5. So let the table do all of this work. So y equals, we got 1/6, that'll be. And then we've got 2x plus 1 cubed. Table set. We'll just have it start at 1, go by ones, and jump to what we need. Okay, first one I want though is a 3. So at 3, I've got 57.16 repeating. That 1/6 repeating is 1/6. Minus, I'll put in the 1. At 1, did I grab the right one there? Yes, I did. At 1, it's 4.5. Subtracting that, I'm going to get 52 2/3. Okay, now the 3 to 5, well, let's see, I plugged the 5 in next. The 5 is 221.83 with the 3 repeating. That's 221, and that fraction is 5/6. Not that you have to use fractions. That's plugging the 5 in. The 3 we already did. That's the 57 1/6. And if you subtract, you're going to get 164 2/3. And okay, so this chunk was 52 2/3. This chunk was 164 2/3. 164. So in reality, when we plug in the 5 and the 1 and subtract those two, we better get what these two add up to. It's the same thing. So if I add these two together, you will get 217 1/3. If I look at my values, does the calculus work? So if I plug 5 in, that's that 221. One was the 4.5. And lo and behold, you will get that 217 1/3. So that area, that consecutive area, the two chunks add up to the whole thing. It all makes logical sense, or just makes sense. And then our last two are shortcuts. All right, even and odd functions with symmetric limits is our last special case to look at. Even and odd functions with symmetric limits, and this is what's key. So, first of all, we'll define what odd functions are, then we'll see what happens with them when the boundaries are symmetrical. So an odd function, if you graph it, it has 180-degree rotational symmetry. So that means if I spin the graph 180 degrees, it looks identical to the way it started. This does not. So, which functions do have that ability? Any function that has an odd exponent. Like x cubed, x to the 5th, x to the 13th. As long as the exponent is odd, the graph will spin 180 degrees and look like itself. Trig functions, sine with its cosecant reciprocal. So the snake, remember the sine graph, looks exactly like a snake when I turn it 180. So that's what that means. Sine, cosecant, tangent, and cotangent are all odd functions. So we need to see what happens with odd functions. -2 to 2. That's what we mean by symmetrical boundaries. One positive, one negative. Let's look at x cubed dx. So if we just do antiderivative, we'll do the power rule. We will get 1/4 x to the 4th, -2 to 2. So plugging in, 2 to the 4th, 2 times 2 is 4 times 2 is 16. 16 divided by 4 is 4. Minus, plugging in a -2, that's still going to give me positive 16. Divided by 4, I'm getting an integral of 0. Let's see why. If you look at the graph for y equals x cubed, it does that little snaky thing like this and like this. And we're looking at the area between -2 and +2. So it's combining these two areas. Well, if you think about it, when it does the antiderivative, this area is coming up positive. This area, because the areas under the x-axis, your height values are coming up negative, it's giving you the exact same area but in a negative value because of its direction. And then they just cancel each other out and you get an integral of 0. So technically, if you wanted to know the area under the curve, you would have to do it in pieces and add them together, or find one of them and double it, but the answer to the integral is 0, because the areas cancel out. So odd functions, symmetrical boundaries, always going to be 0. You don't even have to do the work on those anymore. So, but it's only when these boundaries are symmetrical. What happened on that last example yesterday, we had some of the graph under the axis, some of it above, but it wasn't symmetrical, and we had more below the axis, which gave us that negative answer. Wow. Okay, so now let's see what happens with even functions. So let's define them. Even functions have the y-axis as a line of symmetry. So you can tell they're even when they have an even exponent. X squared, x to the 4th, x to the 10th. And then the trig functions that are even are just the other two, cosine and secant. So let's see what our shortcut's going to be for even functions with symmetrical boundaries. So number 6. Let's look at -2 to 2 again. We need an even function. Let's go x squared. Keep it smaller. All right, so our antideriv is 1/3 x cubed. We'll be plugging in -2 and 2. Plugging in 2 cubed is 8. 8 times 1/3 is 8/3. Minus, plugging in a -2, I'm going to get -8/3. So minus a -8/3. Adding, I'm going to get 16/3. So, the shortcut here, it's not much of a shortcut. Not like the other one where it always comes up 0, but here, what happens is you get -2 to 2. This was 8/3. It's giving you the 8/3 over here and combining, so you're really just getting what's in the first one chunk of it doubled. So their shortcut for even functions, you can, let's go -a to a of f of x. If it's an even function, what they do is they rewrite it and say, oh, I'm just going to do it from 0 to a and double that answer. The only thing that saves you is plugging in a 0 and making your life maybe a little bit easier than plugging in this -2. So not much of a time saver, but it is one. All right, so here's our last. Is it the last? Yes, last one. And don't be afraid. Number 7. -3 to 3. We're going to find the antiderivative of 8x cubed minus 8/9 x to the 5th plus 4 x to the 6th minus sine 10x plus 6 tan 1/2 x. Okay, I'm running out of room, so I'll stop there. Dx. Okay, looks like a lot, but remember, all of the odd functions with symmetrical boundaries, it's going to come up 0. Let's get rid of them. We don't need to work with them. So anything that's odd, you can just cross off before you even start. X cubed, gone. X to the 5th, gone. Even, got to keep it. Is sine even or odd? If you look back, sine was the snake. That one is odd. Tangent is odd. This whole problem comes down to just one term. And if we want to do the shortcut, we will do the antiderivative, which means make this a 7. So we will have 4x to the 7th times 1/7. And then we can go from 0 to 3 and double that answer. So that means I've only got to plug the 3 in. The 0 is going to give me 0. So that doubling and 0 can go away and you can just put the -3 back in. Or the shortcut is 0 to 3, double the answer. So we're going to have 8/7 times 3 to the 7th. And do I have that? Yeah, I do. Big number. 2,499.43. Done.